Hi everyone. In this video, we'll look into diffusion models. Specifically, we'll look into DDPM, which is Denoising Diffusion Probabilistic Models, which is a seminal paper on diffusion models in the image space. We'll dive deep into the forward and the reverse diffusion process and understand the entire math that ultimately leads to this simple formulation of the training objective. So let's get started. The idea of diffusion models is to destroy all the information in the image progressively in a sequence of time steps t, where at each step we add a little bit of Gaussian noise, and by the end of a large number of steps, what we have is a completely random noise mimicking a sample from a normal distribution. This is called the forward process, and we apply this transition function to move from xt-1 to xt. We then learn a reverse of this process via a neural network model, where effectively what the model is learning is to take the image and remove noise from it step by step. And once this model is learned, we can then feed it a random noise sampled from a normal distribution, and it will remove a little bit of noise from it. We then pass this slightly denoised image again and keep repeating this. And at the end of a large number of denoising steps, we'll get an image from our original distribution. If all of this sounded like a very vague overview, not giving any insight or intuition, then yeah, this is exactly what I felt at the start. And then instead of rushing through all the details, I decided to try and understand why we are doing this and what's the reason behind each of those steps, if not from a mathematical standpoint, then at least from an intuitive one. And the first thought that one could have after seeing all of this is what the significance of the term diffusion is in here. To be honest, all I really know is that diffusion is movement of molecules from regions of higher concentration to lower concentration. So what's that got to do with this? And moreover, this looks in some sense very similar to what we do in variational autoencoders, doesn't it? I mean, in VAE, we have an image sample and we convert it to a mean and variance of a Gaussian distribution using an encoder. And then simultaneously, train a decoder that takes a sample from this Gaussian distribution and attempts to reconstruct the image. So it seems like we are kind of doing something similar here, except maybe not in one shot, but through multiple levels, I guess. Then why is this new term diffusion being brought here? And why is this not some variation of VAE? And to answer that, once you look more into what diffusion processes are, these are some of the results that you will get. So stochastic means some randomness involved. Markov, we know, simply means that the future state of the process will depend only on the present state. And once we know the present state, any knowledge about past will give no additional information about the future state. And continuous would mean there aren't any sort of jumps. And you can connect this to our equation of forward process, where we have this Q function, which is honoring this Markov definition. Xt is only dependent on xt-1. This is another one that will come up, and this gives a different perspective. So this states that diffusion is a process of converting samples from a complex distribution to a simple one. And if you try to link it to what we are doing here, then our input image distribution obviously is a complex one. And if our goal is to convert samples from this distribution to samples from a simple prior, that is normal distribution, then this diffusion process can come handy. And this mention of repeated application of transition kernel is again referring to this transition function that we have. And the claim is that this will lead to a normal distribution. We'll soon see why this is the case, but for now, let's just assume it to be true. So diffusion is a stochastic Markov process that allows us to transition from any complex distribution to a simple distribution by repeatedly applying a transition kernel. Let's look at next one. Okay, so my little brain is screaming to ignore this completely. So that's what we are going to do. But wait, let's bring the equation back again. Ignoring specific details, this is saying that diffusion processes would have equations of this form, which is that change in x is a combination of a deterministic term and a stochastic term. And this is also something that we are doing in this transition function. If we apply the reparameterization trick, we get this. And if we simply add and subtract xt-1, we'll get this. Here also, we see that the change, which is xt minus xt-1, is again a combination of a deterministic and a stochastic term. So clearly, while the end objective is very similar to what we have been doing in VAEs, but we are modeling the process of reaching that objective very differently. And in fact, it is modeled behind ideas of physics specifically pertaining to that of diffusion processes, hence the term diffusion. And the hope is that modeling it this way will lead to better generation results than VAE. Now it seems that the center focus of this diffusion process, specifically the forward, where we move from image distribution to normal, is this transition function. And somehow applying this repeatedly converts an image, which is a sample from a very complex distribution, to a sample from a normal distribution. So why is this transition function achieving that effect? And first, let's not even bother using some relationship between the coefficients. Let's try with alpha and beta, where they are independent of each other. The way we'll go about it is we'll start with this distribution, which is not really complex, but that's okay. We'll sample some numbers according to this distribution and chart out a histogram plot. Then we'll apply whatever transition step once. This will lead to a change in the values and hence a change in the histogram plot. Let's say this is the values we use, so we'll get this histogram. Then connecting the bar midpoints and having a sufficiently small bin size, we can actually approximate that this is our change distribution. And effectively, what we are saying is that applying this transition function once changes the left distribution to the right one. Now, obviously, we can say that with alpha equals 0 and beta equals 1, in one shot itself, we are at a Gaussian. But that's not much useful, is it? What we want to do is gradually shift the distribution to a Gaussian, making slow progressive changes, if we really want to model the transition as a diffusion process, just like how dye would slowly distribute in water. Let's first try with alpha. We can see that setting alpha to values of anything greater than 1 will never allow us to reach our goal, because the variance will end up blowing soon enough. Hence, having some decay in the original distribution values is necessary. We can try with a value just smaller than 1 for alpha, but what about beta? We need to slowly introduce this noise term, and having higher values of beta will never allow us to do that. And moreover, it will end up making sudden changes in the distribution. And we also don't want that. We want slow transitions, and the more of original distribution we have destroyed, the more it should look like normal distribution. When we put in these values, this is exactly what we get. Smooth transition between each steps, and slowly the distribution changes to a Gaussian. Let's mathematically see why this is the case. This was our transition function for the forward step that we started with, where we are formulating xt in terms of xt minus 1. Starting from the last time step t, we can write xt minus 1 in terms of xt minus 2 using the same formulation. Separating the xt minus 2 term and everything else, we get this. We can already see a pattern that's recurring, but let's do once more the same steps. This time replacing xt minus 2 in terms of xt minus 3. Since each time we only get one term involving xt and the rest are all independent of xt, repeating this for all time steps, we'll end up with this. Only the first term has x0. And when t is a sufficiently large number, this term will be very close to 0 because all the values in the product are less than 1. The rest of the terms are all Gaussians with 0 mean but different variances. However, since all are independent, we can formulate them as one Gaussian with mean being 0 and the variance being sum of these individual variances. So this guy will have a variance of beta, this one beta times 1 minus beta, and this one will have beta times 1 minus beta square. So this becomes a GP with the first term being beta and the factor that is multiplied with is 1 minus beta. Hence the sum for t terms will be this. And this ends up being 1. Hence this transition function indeed ultimately will lead to a mean 0 and unit variance Gaussian. By the way, if you would have noticed, I conveniently went from putting uncorrelated coefficients alpha and beta for both the terms to related coefficients, square root of 1 minus beta and square root of beta. This was because that is what the authors use. But even if you go through with this proof, with square root of alpha and square root of beta terms under the same constraints, that is alpha just smaller than 1 and beta a very small value, we'll end up with the first term being this, which will again vanish for large t and alpha less than 1. The variances are this for the first, second, and third term, and so on and so forth. Again, a GP, but now our GP sum will be this. So mathematically, the relationship between alpha and beta comes out from our requirement of final sum of variances to be 1. Intuitively also it makes sense as you are effectively correlating the amount of structure of original distribution that you destroy with the amount of noise that you add. That's all that I could think of, but do let me know if you think there's more to the reason of relationship between the scaling and the noise variance terms. What we did here was discretize the diffusion process into a finite steps for a 1D distribution. We can use the same principles to do it for a W cross H image, and the output for the forward process will then be a W cross H image where each pixel is identical to a sample from a Gaussian distribution of mean 0 and unit variance. In practice, we don't use a fixed variance of noise at all steps, but we instead use a schedule. The authors use a linear schedule where they increase the variance of noise over time, which makes sense if you think from a reverse process standpoint, as when you are at the start of the reverse process, you want the model to learn to make larger jumps, and when you are at the end of the reverse process, you are very close to a clear image, you want it to make very careful small jumps. Another benefit that I could see is that the schedule actually allows the variance of the distribution to progressively scale very smoothly, from the input to the target Gaussian. This is the plot of variance of our not so complex distribution throughout the time steps of forward process. You can see that with fixed noise, our distribution variance reduction is larger at the start. And after only about 500 steps, it reaches very close to 1. And only minor changes post that. Whereas the reduction is much more progressive and is more uniform for larger fraction of time steps when we use a schedule that the authors suggest. There's another good property of this equation which I should cover before we move away from the forward process of diffusion. Because we want to have the process run over close to 1000 steps, then we are essentially requiring that for t equals 1000, we have to apply this equation 1000 times to go through the entire Markov chain, which is not really efficient. However, it turns out that we don't really need to. So we have this as the formulation of xt. And now let's define 1 minus beta t as alpha t, allowing us to write xt as this. Now we can do the same recursion that we did few minutes back. We can put the expression for xt minus 1 in terms of xt minus 2 using this transition formula. Separating xt and non-xt terms, we'll get this. Like before, this is adding two independent Gaussian noise with variances 1 minus alpha t for this term and this for the other term. And they can be rewritten as one Gaussian with variance equal to the sum of these variances. Alpha t's will now cancel out each other. And doing the same for xt minus 2 in terms of xt minus 3, and then again separating xt and non-xt terms, we'll get this. We can see the pattern that's coming up, and if we repeat this till x0, what we'll get are these two terms. So we are going to define this cumulative product of alphas from I is equal to 1 to t as this term, and then we can rewrite the last equation as this. And finally, we see that we can actually go from the initial image to the noisy version of the image at any time step t in the forward process in one shot. All we need is this cumulative product term, which can be pre-computed, the original image, and a noise sample from normal distribution. Now, although we covered a lot of math, but if you take a step back and see, then all we really did was convert image to noise. And you would agree there are simpler ways to do that. So why go through all of this? How does modeling this forward process benefit us if ultimately all we did was convert it to noise? Well, it turns out that under certain conditions, which are met here, the reverse process is also a diffusion process, with transitions having the same functional form, which then means that our reverse process, which is actually generating data from random noise, will also be a Markov chain with Gaussian transition probability. But we can't straight away compute it because that would require computations involving the entire data distribution. However, we can approximate it by a distribution P, which is formulated as a Gaussian whose mean and sigma are the parameters that we are interested in learning. This formulation can be done because we know that the reverse will have that form according to the theory. Now here I did not go into the details of why the reverse is also a diffusion with Gaussian transitions, because frankly I don't know. I'm guessing this would have roots into some theory of stochastic processes, but if somebody knows an intuitive answer as to why the reverse is a diffusion process, do let me know in the comments. I just told that we can't compute the reverse distribution, but we'll somehow approximate it using P. Let's now look into how do we do that. We have a similar situation in VAE where we don't know the true distribution of x given z, but we learn to approximate it via a neural network. Let's just quickly see that and try to apply the same methods for learning our reverse distribution here. We want to learn P of x given z such that we are able to generate images as close to our training data distribution as possible. And for that, we try to maximize the log likelihood of the observed data. So we have log P of x, and we can rewrite it as marginalizing over the latent variables. We can then multiply and divide by a distribution Q of z given x inside the integral to get this. So this is nothing but log over expectation of this quantity under the distribution Q of z given x. And because log is a concave function, we can see that log of expectation of something is always greater than the expectation of log. And using this fact, we can get to the lower bound of the log likelihood of our data. And instead of maximizing the likelihood, we can maximize this lower bound. Once you expand the terms within the lower bound, you get these terms. The first term here, with the assumption that P is Gaussian, ends up being MSE or reconstruction loss between the generated output and the ground truth image. And the second term is the KL divergence between our prior, which is mean zero and unit variance Gaussian, and the distribution that encoder predicts. The same line of thought can be extended to our diffusion case, where you can think that now, instead of going to ZT in one go, we move through a sequence of latents x1 to xt. And our Q of z given x is now Q of xt given xt minus 1, and it's fixed and not learned. So again, we want to maximize the likelihood of the observed data, which is log of P of x0. This is equivalent to integrating out everything from x1 to xt from the joint distribution of the entire chain. And applying our inequality for concave functions, we get this, which is our lower bound that we'll maximize, which is kind of what we got in the VAE case as well. But up until now, we haven't really used the fact that both forward and reverse are Markov chains. Let's now do that. This was the term inside the expectation. We can do that for P as well as Q because both are Markov chains. Here Q is our forward process and P is the approximate for the reverse process. Notice that this conditioning on x0 is actually doing nothing. And since the forward process is Markov, we can remove it as Q of xt given xt minus 1 and x0 is same as Q of xt given xt minus 1. But we'll keep it and we'll soon see that this actually ends up helping us. Let's first look at the denominator part. On the terms inside the product, we can apply Bayes' theorem to get this. Then after expanding, you will see that all the xt given x0 terms cancel out, like this and this, and even x1 given x0. All except the term involving the last time step t. So only terms in the numerator remain, and specifically what's left are these xt minus 1 given xt comma x0 terms, and this one term xt given x0. So we can rewrite the denominator as this and put that in our lower bound equation. Now we can separate the x0 given x1 term from the numerator and separate this entire thing into sum of 3 log terms. Remember, all of this was under the expectation of Q. Now this is very similar to the VAE lower bound. The first one is like the KL divergence prior term, but here because we are using diffusion, Q is fixed, and the final Q of xt according to theory will actually be very close to normal distribution. So this is parameter free, and we won't bother optimizing this. Second is reconstruction of our input x0 given x1, and the last term is a sum of quantities which are nothing but KL divergence, actually negative of KL. And since we want to maximize the lower bound, we want to minimize all of these KL terms. The good part about this formulation is that the last term involves two quantities of the same form. And this is simply requiring the approximate denoising transition distribution to be very close to the ground truth denoising transition distribution, conditioned on x0. At first glance, it might look like we are back where we started, but that's not the case. Instead of Q of xt minus 1 given xt, we have additional conditioning on x0. And intuitively, this is something that's easier to compute, because once you look at the original image, you can have some sense as to how to go about denoising this image from one time step to previous time step. In fact, we'll compute this quantity next and we'll see that it has a very nice form. We can use Bayes' theorem to rewrite this quantity. Now each of these are Gaussians and we have already computed them. The first term is our forward process, and although it's conditioned on x0, but that's going to have no impact because our forward process is a Markov chain. The other two terms can be written using the recursion that we established earlier, which allows us to go from x0 to a noisy image at any time step t. Because these are all Gaussians, we can write them in this exponential form. And now our ultimate goal is to compute distribution of xt minus 1. And our hope is that somehow we can convert this into a perfect square, allowing us to get the equation for some Gaussian distribution. So with that motivation, we'll separate xt minus 1 square terms and xt minus 1 terms and everything that is independent of xt minus 1, which is what we have done here. Xt minus 1 related ones are within the first two terms, and everything not involving xt minus 1 is wrapped within this last parenthesis. So these would be xt square term coming from first, x0 square term coming from second, and all the terms coming from this guy. Combining both terms for xt minus 1 square, we get this, and combining both for xt minus 1 will give this. Now because our motivation is to get just xt minus 1 square, we'll factor out everything that is multiplied with it from all terms here. And to allow to do that, we have multiplied and divided the last term with this. So up till now, we wrote the normal distributions in the exponential form and some algebra to get this. Now we'll work on the final term, which was everything that is independent of xt minus 1. And like I said before, these will be the xt square term from this, x0 square term from this, and everything in this. And after we have simplified these terms, we'll notice that it's exactly the square of this term that is multiplied with 2xt minus 1 here. The first two are the square terms, and the third is their product. This allows us to rewrite the whole equation for reverse distribution as a Gaussian, with this being the mean and this being the variance. All of this that we have done is because these were our likelihood terms that we had to optimize. And for the last term, we need to compute q of xt minus 1 given xt, x0, which we have done now. If you take a closer look at the mean, then it's kind of a weighted average of xt and x0. And if you compute this weight for x0, then you will see that it is a very low value at higher time steps. And as we move closer to the end of the reverse process, this weight increases. And from the graph, it might seem that the weight is just 0 for a long time. But when you actually plot the log values, you can see that there is indeed an increase over time. Coming back to our reverse diffusion process, this is what we need to compute. We obviously have to approximate it because for generation, we won't really have x0. But because we know that our reverse is a Gaussian, we can have our approximation also as a Gaussian. And all we need to do is learn the mean and variance. The first thing that the authors do is fix the variance to be exactly same as the ground truth denoising step variance. Now remember, our log likelihood terms were these, and all of these under the expectation of q, making it KL divergence. And when you use the KL divergence formula for Gaussians, because here both the distributions have the exact same variance, it will end up being the square of difference between the means divided by twice the variance, which is this quantity. So since our goal is to maximize the likelihood, we need to reduce this difference. Now because our ground truth denoising step has mean in this form, we can rewrite the mean for our approximate denoising distribution also in this form. However, since we don't have x0, we'll approximate it by x theta. So at any time step t, x theta will be our approximation of the original image based on what xt looks like. And once you formulate mean as this, KL divergence, which was earlier square of the difference of mean, will end up being this. We scale down by twice the variance, which was already present, but we also need to scale by square of everything that x0 and x theta are multiplied with. So after all the maths, we end up with the loss term being how well our model approximates the original image, seeing a noisy image at time step t. This is a valid formulation of the loss term, but authors actually formulate loss as how well our model approximates the noise that was used, which can actually be derived from what we have here. So let's see that as well. If you remember, we had seen xt can be written in terms of x0. And in this equation, we can move x0 to one side, which gives us a way to rewrite x0 in terms of xt and original noise added. And now we can use this to reformulate the mean. We can replace x0 with this guy, and after some simplification, we'll arrive at this quantity. Now we have expressed our ground truth mean in terms of xt and the noise sample added. We can similarly rewrite our approximation of mean as xt and noise prediction. And now our mean differences will become square differences of the ground truth noise and the predicted noise. We'll still have twice the variance in the denominator, as that's coming from the KL divergence formula, but we'll also have to multiply with whatever factor the noise term in the mean was multiplied with. After doing that, we'll finally have this loss term, which is exactly what the authors also mention in the paper. So to recap, from our likelihood terms, we ignored the first one because it did not have any trainable parameters. Upon working on the individual terms in the last summation, we identified that it can be written as scaled square difference between the ground truth noise and the noise prediction generated by some model using xt as input. In practice, we also provide time step as well to the model, but that is something we'll anyway cover in the implementation video. The authors actually ignore the scaling altogether and through experiments find that just training a model on the squared difference of noise is good enough. Even the second term in likelihood is also wrapped under this loss by having the model approximate the noise that was added to x0 to get to x1. During training, t equals 1 is treated as same as any time step, and the only minor difference happens in sampling, which we'll see soon. Now that we have covered every bit of math involved and reached our simple objective to optimize, let's see altogether how we train this. During training, we'll sample an image from our dataset and also sample a time step t uniformly. Then we sample a random noise from a normal distribution. We use the below formulation to get the noisy version of this image in the diffusion process at time step t. The original image and sampled noise are used, and we use the time step and our noise schedule to get the cumulative product terms, which we can also pre-compute. The noisy version of this image is then fed to our neural network, and we train the network using the loss to ensure that the predicted noise is as close to actual noise as possible. Training it for a large number of steps, we'll cover all the time steps, and effectively we are optimizing each individual member of this sum term. For image generation, we need to go through the reverse process, and we can do that by iteratively sampling through our approximation of the denoising step distribution P that our neural network has learned. For generating, we start with a random sample from a normal distribution as our final step T image. We pass it to our trained model to get the predicted noise. And just to reiterate, our approximate denoising distribution was this, and we formulated the mean this way using noisy image at time step T and predicted noise. If you simplify the terms, you end up with the mean image of the denoising distribution as this. Once we have the predicted noise, we can sample an image from this distribution using the mean image and the variance, which was actually fixed to be same as the forward process, and this becomes our xt minus 1. Then we just keep on repeating this process all the way till we get our original image x0. The only thing we do differently is we return the mean image itself to get from x1 to x0. And that's it for training as well as the generation part for the DDPM diffusion model. With this, we come to the final question of this video, which is why even create this video? And specifically since I am not an expert in diffusion models. In fact, on a scale of 0 to 1, since all I've spent is about 500 hours of understanding diffusion models, I would peg myself to be somewhere right about here. But the whole reason for this video is to make whatever little number of people are on my left a bit more knowledgeable of what's happening in the diffusion process. And there's a selfish reason as well, which is I wanted to dive deep into every little detail that I can think of, and making this video ensure that I do that. And also so that people on my right can pitch in and improve my understanding wherever my explanation was missing something. This entire video would not have been possible had these amazing people not invested their time in creating resources which help me understand things a lot better. So big thank you to them. Do take a look at these, links are in the description. And in the next video, I'll get into the architecture and implementation of DDPM. So see you then.